It's time for my third presentation. Today I will talk about some algorithms for visibility-based pursuit and evasion. And I know many of you have seen these things before, but I suspect that some of you perhaps have not. So I'll start with some very basic problems and then describe some newer results from my group that have made some progress on these kinds of things. Okay, so today, pursuit and evasion. Now, so the basic idea of these kinds of problems is that we have some robot, or maybe multiple robots, that are moving through an environment, and the goal is to catch some other agents that are moving around. So these other agents may be bad guys, in some sense. We can also think of other kinds of applications. So. Okay, so there's some bad guys we could try to catch. Perhaps there's a museum we want to patrol and guarantee that there are no bad guys in the museum. But another very interesting kind of application for this line of thinking is to assume that the evaders that we want to catch are not necessarily antagonistic, that they're not our enemies, but they perhaps are victims in some disaster and they need some help. And we want to guarantee that we can find all of the victims that need help, right? So, for example, in the United States, about 10 years ago, we had a huge disaster called Hurricane Katrina, and actually it took a very long time to find all of the victims of this disaster. In some cases, maybe even a week after the hurricane came, they're still doing some searching, right? So we would like to think about algorithms that robots can use to figure out how to move through their environment in a way that guarantees they can see all of the other agents that are in the environment. Okay, so turns out this problem has been studied very carefully and actually for a long time, right? So you can see some of the oldest papers in this family go back even to the 60s. Okay, so here's the basic problem. We have some environment, and it's a known environment. We can describe that environment. Well, let's just keep things simple and say that the environment is a polygon. Later on, we maybe can imagine polygons that have holes. But for now, let's suppose we have a simple polygon that our robot is moving through, and let's suppose that robot has a range sensor, so the robot can see its own visibility polygon. So anytime the evaders come within the visibility polygon of the robot's position, we can see them, and we declare victory at that point, right? So in particular, perhaps some of you are familiar with other kinds of problems where the goal is not just to see the evaders, but actually to catch them, to move very, very close to them. And we're considering that a separate problem, right? So you might imagine running these kinds of algorithms first to find out where the evaders are. Then we can zoom in and try and physically catch them if we want. Okay, so our goal here is to see the evader. And again, we'll keep things very, very simple. We assume we can see in all directions and with as long a distance as we want. Okay, so there's our problem statement. And here's one other fact that perhaps will seem ridiculous. We're going to allow the evaders to move as fast as they want. I'll pause for effect here, right? And so we're assuming evaders that, well, here's the idea. Perhaps we don't know very much about what the evaders can do, right? So if we have no model of their motion, we don't know their patterns or their maximum speed or any of these kinds of things, we're just going to let them go as fast as they want, right? So as long as they're not teleporting from one place to another, right? So we do constrain them to move along a continuous path, but we don't constrain their motion speeds at all, right? And so this has, so in addition to helping us avoid the need for a specific model for how the evaders move, in many ways this actually makes the problem easier for us, right? So it doesn't look like it, but this is actually a simplifying assumption, right? The idea is that if the evaders, for example, have maximum speed, then the algorithmic problem of keeping track of where the evaders might be becomes much more challenging, right? We can end up with some very strange shapes as as possible positions for the robot gradually expand across the environment. In this case, we can essentially treat the evaders like a gas that expands instantly to fill any space that we're not watching carefully. Right? So this is the problem statement. Is it clear? Everybody see where we're trying to go? Right? Okay, so we would like to think about these kinds of problems. So the input is a simple polygon describing our environment, and the output should be a path for a pursuer to follow, along with a guarantee that if the pursuer follows that path, that any evaders in the environment will be within the visibility polygon of the pursuer at least one point along that path. Right? Okay, so that's where we want to go. Now, before I start to describe some new results, let me show you the classical solution to this. Let's see, so this is, I've got it here instead, actually. So the solution is due to Givas, Latome, Laval, Lin, and Matwani, abbreviated hereafter GLLLM. This is from, actually the original workshop version of this paper was from, I believe, 1996. The final version from 1999. So here's their idea. First thing is to notice that we can say some very strong things about where the evaders might be. Right? So we saw this idea of gaps actually a few days ago, and perhaps surprising, perhaps not, but it shows up here again. Right? So here's an example visibility polygon. I believe this is the same one we saw a couple of slides ago. And one observation you can make is that if we assign just one bit to each of those gaps, that is enough to encode all of the information the robot might have about where the evaders are. Right? So you remember, I hope, that each one of these gaps corresponds to a region of the environment that we can't see right now. Right? And I hope you'll remember that since this is a simple polygon, that each of these sort of hidden shadow regions, that they're all distinct. Right? They don't connect to one another. So that means that the only information we need to keep track of for each of these gaps is thumbs up or thumbs down, right? Is there an evader back here? Yes or no, right? And we'll write those as zeros or ones, right? So anytime we label a gap edge with a 0, that means based on what's happened in the past, we know for sure that there's no evaders hiding behind that gap edge. And if we label a gap edge with a 1, that means we don't know. Right? So 0 refers to cleared, and 1 we'll call contaminated. Right? Contaminated, again, meaning maybe there's evaders there, maybe not. We don't have enough information. And so from there we can kind of see some flavor of what the algorithm should look like. Right? We have our pursuer robot starting in some position, and we want it to move around. And from that starting position, let's label all the gaps with 1s. Right, saying we don't know where the evaders are, so they could be behind any one of those gap edges. And we'd like to move around in such a way that those labels turn all into zeros. Right? If we have all zeros, that means that any evaders that might have been in the environment, we've seen them. Right? So when we get to all zeros, we're done. Right? So we start with all 1s, move around, and we want to get to all zeros. Right? So that's a bit of progress, but there's one important detail that is sort of difficult here, and it's the fact that we're still looking for a continuous path. Right? We're looking for a path through a polygon that doesn't necessarily need to go from vertex to vertex or along the boundary or any of these kinds of things. So the space of paths that we might consider is very, very big, right? So there's perhaps some of you have better math training than I do, can say something stronger about this, but there are sort of infinitely many different paths that we could consider here, right? And as a computer scientist, that's problematic for me, right? I don't like to write for loops that have infinitely many iterations to them. Those don't tend to finish ever. So what we need is a way of turning this continuous problem into a discrete problem. And okay, so there's another example here, right? I forgot this was here. So this one has 1, 2, 3, 4, 5, 6 gaps, right? And again, we assign a label for each one. Okay, so if we want to make this problem change from a discrete problem to change from a continuous problem to a discrete one, then we need to sort of think very carefully about how the gaps can change, right? And it looks like I needed to draw some thicker lines because the most important parts of the slide turn out to be invisible to you, I think. So But I think that's okay. We can get through this. And this is actually very similar to what we talked about a few days ago, right? So we're thinking about these gaps, and as the robot moves around, those gaps can change. And if you remember back that far, we identified four different kinds of events that can happen to change the gaps, right? So we can have appear, disappear, split, and merge events. And just as we saw with the gap navigation tree, those kinds of events can occur here as well, right? So for example, well, maybe I can just ought to redraw it here, I suppose. So I'll just go through this very quickly, since I think the idea is fairly simple, and it's one that we've seen before. So for this kind of environment boundary, if our pursuer is here, then we can draw a line that tells us when this gap here disappears, right? So from here, we've got a gap here, right? We can't see here. And as the robot moves this way, once it crosses this line, the gap disappears, right? Appear events happen in reverse, right? So these figures are always actually pretty easy to draw, since disappear and appear are opposites, right? So we can get appears and disappears, and we can also get splits and merges, and I could just kind of give you some intuition for where those happen. So for example, a robot right here will see two gaps. Right, so the robot can't see in here, we can't see in here, right? But any evaders that are in here have to stay in here. They can't get over here, right? So the evaders' possible positions are partitioned into those two groups. If I take the line that connects these two peaks and extend it outward, right? So two rays parallel to the line connecting those peaks. If we go down here, then there's only one gap. So we get that kind of merge, right? And at that point, the evaders can sneak through, right? So anybody who had been here can hide here, right? Okay, so that's the idea. So as the pursuer moves around, the gaps can change. But I guess the interesting thing here is that we can draw in some line segments that indicate where those changes can happen, right? And of course, if you've studied the right kinds of computational geometry, you may recognize this as being very similar to visibility cell decomposition, right? Yeah, and that's exactly where we're going. Yeah, it's not quite a visibility cell decomposition because there's some edges we can leave out, but that's the basic idea, right? So we get these appear, disappear, split, and merge events on our gaps. Right, so we can do a cell decomposition based on those things. The basic idea is just to take every reflex vertex and draw rays out that are parallel to those edges, right? So that happens here. I showed you one, but there's also another decomposition edge here, right, corresponding to a gap in this region appearing or disappearing. And the same thing, to find out where split and merge events happen, we take each of the bitangents in the environment and extend rays outward from those, right? So, and then for each one of these, when we cross in one direction, it'll be either a split or merge, and then coming in the opposite direction will be the other one, right? And we can compute which event is happening when we cross each one of these things, right? So there's a lot of details on here, but the basic idea is that we can draw these rays into our environment, and it's if you like a series of ray shooting queries in that environment to decompose it into a collection of O(n) squared cells. Now, why are those cells useful? Well, here's the idea. I want to claim that each one of those cells is a conservative region. And by conservative region, I mean that if a robot moves around within that cell, if we have some closed path starting at one point, staying within that cell, and going back to the starting point, I want to argue that the information available to the robot, the set of possible states for the evader, to think about it that way, the set of possible states for the evader will be the same, right? In other words, unless I leave one of these cells, nothing interesting happens, right? So the proof in the paper is this is one of these things that is sort of feel like you're chasing your tail a little bit, because once you believe that this decomposition captures all of the events that can happen, then, well, of course, nothing interesting can happen when no events happen, right? So, but maybe you can get some of the intuition here, right? So here's the decomposition I described for a very simple environment. And so suppose the robot is here, right? So it's in this sort of central rectangular conservative region. And there's two example paths shown, right? One in which the robot moves around but does not cross any of the conservative region boundaries, right? So in that case, if the evaders were up here, the shape of this particular gap will change a little bit, right, as the robot moves relative to this reflex vertex. But if there are evaders in here, then they can make sure to hide far enough up here that we don't see them, right? Right, so if we stay within this conservative region, then nothing interesting happens, and we're back where we started. Right? On the other hand, if we leave this conservative region, so shown here, if we cross that critical boundary, then at that point the gap disappears, right? And when we return back to our original location, the gap will be there, but at that point we know there's no evaders hiding right there, right? Because we just checked. Right? So that's the idea. That's kind of the argument for why this decomposition into things that are very much like visibility cells. That's why this decomposition is in some way the right one, right? Because it's the minimal set of divisions we can make that gives us this property, where staying within one cell of the decomposition gives us conservative regions, right? So this is very good news, right? Remember, we were concerned for a few moments that we had a continuous problem. We had a very huge space to search, right? We were thinking about the set of all paths through the environment, well, through the interior of the environment even. So that's very bad news, but now we've got a handle on it, right? The fact that these regions are conservative tells us that we don't really care about exactly what the path does. As long as we know which sequence of conservative regions are visited, then none of the other details really matter for the purposes of this pursuit evasion problem, right? So that's a good thing, right? Okay, so from there we sort of have all the pieces that we need to be able to solve this problem. Right? The idea is, well, as it always seems to, as we form a graph. Let me be very careful about how I describe the graph. We form one vertex in the graph for each combination of a region, along with a set of gap labels for that region. Right? So for example, in this top left region, if the robot is here, then there's exactly one gap, right? It sort of corresponds to the part of the environment that's hidden behind this reflex vertex, right? So down here, sort of chops off a part, and the pursuer can't see anything up here when it's in this region. Right? So since there's just one gap, we have 2 to the 1 vertices there. One labeled 0 for clear, one labeled 1 for contaminated, right? And so on, right? The most complicated one we get in this very simple example is in the center, where we have 2 gaps at that point, right? One on each of the top segments of the environment. So we need to keep track of all 4 of those possibilities, right? Could be that both of them are contaminated. Maybe one's clear, the other one's clear, or maybe they're both clear, right? So we form this graph showing all of the different combinations of position, of conservative region location, and gap labels as well, right? And so we can form this graph. The edges, well. Right, so there's 2 things that need to happen. One is that we only draw edges between conservative regions that are adjacent to each other. I think that's pretty obvious. Our pursuer robot, of course, does not teleport, right? So it can only go from one conservative region to an adjacent one. But then when we're drawing that edge, for example, let me find a good example. For example, from here, if the robot is at this node, we can go to this conservative region. But which one do we connect it to? Right? So it turns out that we need to describe update rules for each of these four events, right? And it's not too hard to do, right? So if we get a disappear event, how does the gap label change? Well, the gap has gone away, right? So we just delete the label for it. So that's easy to do. What happens if a gap appears? Should be clear, right? So if a new gap appears, that corresponds to a place that just a second ago we were looking at. We know there's no evaders there, so we mark it cleared. Right, if a gap splits, then we don't know which side the evaders will hide behind. Right, so whichever label we had for the for the gap before the split. We assign that same label to the two gaps after the split. What about a merge? Well, in that case, we take the worst case, right? So if they're both contaminated, then we get contaminated. If they're both clear, it stays clear. Otherwise, it's contaminated, right? So we can actually define this very short set of rules for how the gap labels change. And all of a sudden, we're done, right? All of a sudden, we've solved the pursuit evasion problem, right? So you can pick your favorite, so we can compute the decomposition, build this graph over it, and then pick your favorite node as the starting location for the robot. Then we're just searching for a path, right? So whichever conservative region is the start location for the robot, we choose the node in that conservative region that has all ones, right? That's uniquely defined. And we search for a path through that graph for a path to some node that has all zeros, right? If you want to be really picky about it, I suppose you could search for a path back to the same location, but with all zeros, right? And that's it, right? That gives us a sequence of conservative regions we should move through. And well, I guess we need to make the path continuous again, right? So given that sequence of conservative regions, well, it turns out all those cells are convex. So it's perfectly safe, for example, to choose the centroid of each cell and draw line segments connecting them, right? We can be sure that will keep us out of the obstacles if we do that. Is it clear how this works? I mean, I know many of you know this already.
How are you sure that such paths exist?
No. In fact, it's not too hard to draw examples where no such path exists. So this is worth doing, I suppose. Well, let me say before I draw it that no political message is intended by the polygon I'm drawing, but it always seems to look like I have one in mind. So sorry. Yeah, even better. Right, okay, so let me add some hooks on the end. Okay, so I hope you can see that in this case no path will exist, right? So the argument is actually fairly easy to make, right? So well, I have to clear one of these four first, so arbitrarily I'll pick this one. So I have to get up to here. Then I go back. Now I have 3 left to clear. So maybe I pick this one next. But when I clear this one, these 2 are contaminated, right? And I have to go far enough up here that I lose vision of this one, right? So, aha, the bad guys were here, and now this one is recontaminated, right? And any sequence you try to use to clear these 4 branches, you can actually need to practice drawing it with 3 because that's significantly less suggestive and it still works. You only need 3. But that's the idea, right? So we cannot guarantee that a path exists. In fact, it's not too hard to make some polygons where no path exists. But what we can say about this algorithm is that if a solution exists, this algorithm will find it, right? So we shouldn't feel too bad about the fact that there are some environments this algorithm can't solve, because if this algorithm can't solve it, then no other algorithm can solve it as well. Is it clear?
I think I saw some algorithm with more than one robot.
Okay, yes, we'll talk about more than one robot in a minute, right? So if you have multiple robots, then there always exists a number of robots that can clear the environment, right? Off the top of my head, surely you can do it with n over 3 robots for an environment with n vertices, right? So in the limit, it starts to look like art gallery kinds of problems, right? So just have the robots all stand still, triangulate the environment, assign 1 robot to each polygon, and certainly you can do it that way, right? And you can, there are bounds. I'm not sure I've seen an environment that requires n robots to solve. But for environments with holes, for example, you can get you certainly can design environments that need at least, say, square root n robots. But so far, just 1. Okay. Any other questions I can answer here? Okay. So before I move on from this problem, I want to show you an example that I find absolutely fascinating. Okay, yeah, so we already talked about that. So it looks like this. So here's an environment here's an environment that can be solved with just one robot, but it takes a long time. Right? So here's the idea. For some reason, we usually describe this as an eagle or as a bird, although it's sort of a mutated one because it has more than 2 legs. Right? In fact, it has, K or 2K legs. The idea is that our pursuer will have to come down into each of these legs to clear each one, and that in between each of those visits to a pair of legs, the robot's actually got to go all the way back up to the top to clear the bird's beak, right? And you have to draw it carefully, but it turns out that if you don't do that carefully, if you don't re-clear the beak every time, then you won't get a solution to this problem. Right? So the only solution to this problem is one in which that peak up there gets recontaminated again and again and again. Right? So there was speculation about this problem for a while that perhaps the idea of a recontaminated gap should not happen. Right? That if you can solve a problem, then you can solve it without recontaminating. And it turns out to be not just false, but spectacularly false. Right? We can get not just one recontamination, but I can give you a family of environments where you can drive the number of required recontaminations arbitrarily high. Right? So this is, in some sense, a pathological case for this kind of problem. Okay, is there a question I'm seeing, or should I keep going? Okay, so this is the way things stood for actually quite a long time. About 10 years or so. This was sort of the best that was known for this problem. But the one thing you'll notice about the solutions you get was that, as I said, to generate this continuous path at the end, you end up visiting a sequence of centroids of conservative regions. And what my student Nick Stifler and I wanted to ask, actually, let me give proper credit. What Nick suggested was maybe we can solve this optimally. Right? Maybe there's a way to find paths for this kind of problem that are the shortest paths that still have this property of catching all the evaders. Right? And I guess I'm leading with the final answer here, but it turns out the answer is yes, we can compute them. Right, so here's an example of, in this environment, starting from this location, the final, or the optimal path that solves this problem. Right? So starting here, we travel here, and you notice we go just until we hit this critical boundary to clear these 2 gaps. Right? And then we come back and around, and you can kind of get the intuition. Right? It comes up here, and it's in some places a little tough to read because the path overlaps itself. But I think you get the intuition. Right? Then once we get to the end there, precisely at the moment when it crosses that last division, we can stop. Right? We know that we've seen all the evaders. So the question is, how do we generate such paths? Okay, so there's one tool we need to get that done, and it's based on this idea. Well, in the computational geometry community, was referred to as a sequence of polygons. We can actually simplify that quite a bit and think just about a sequence of segments. Right? So here's the idea. If you decide what sequence of conservative regions you're going to visit, then the question you might ask is, what's the shortest path that visits those conservative regions in that order? Right? So this is not solving the whole problem. This is just, given some regions in sequence, what's the shortest path that visits those regions in sequence? Right? So our problem is a little bit simpler than the algorithm that's in the literature because we know that the polygons we're visiting are touching each other, right? Each consecutive pair shares an edge, right? So we can actually just ask, given a sequence of segments, right, which are the edges shared by the regions we're visiting, given the sequence of segments, find the shortest path that visits those segments in the order that they're given, right? So, and actually, just to be clear, the fact that they're given in order is absolutely crucial to the fact that we can solve this efficiently, right? So if we don't have the order, then it looks like a traveling salesman problem, and everything has gone wrong, right? Okay, so you see the idea. I will omit the algorithm for solving this and simply say, we can do this efficiently, right? And it's not bad, right? Nick actually wrote some code for this. The basic idea is a is a partition of the plane into regions where the combinatorial structure of the shortest path is constant within each region. Right? Okay, so that's what we want. So let's suppose we have a subroutine that can do this. Based on that assumption, how can we proceed? Well, the basic idea is good. Basic idea is just to do a forward search. Right, so the nodes in our forward search will correspond to nodes in our original graph. Right? So we'll keep track of both conservative regions and these gap labels, and we expand forward. And it turns out to make it work, the tricky thing is finding a way of knowing when to stop. To find a way of knowing, here's a new solution, but I thought of something better before. Let me stop going down in this direction and continue in another direction. Right? Yeah, I mean, if you've this to me has a bit of an AI kind of flavor to it, where we're searching for a path through a graph via some forward search. Right, we're not building the whole graph ahead of time, and we need to find the right way to know when to stop any particular thread. Okay, so here's the interesting part. So the question is, given two sequences of conservative regions, when can I say for sure that I can throw one of those away? So suppose I have two of them. So they're shown here as R1 through Rm-1 and S1 through Sn-1. And then the last two segments, Rm and Sn, end up in the same conservative region. Right? They may end up at the same segment, maybe not. So we consider they're going through some possibly distinct paths to get to the same conservative region, maybe through a different number of steps and so on. And the idea is, I want to give you a condition for when I can throw away segment sequence S. And one very simple way to get that is to say, suppose I followed this path from this is written a little strange. There's kind of two versions of this, and I'm halfway through describing one version, so ignore the text here for a second. The idea is very, very simple. So if I want to think about throwing away segment sequence S, well, one way I could do that is if we can say that R is strictly better if I can follow all the way through R, then jump to S, right, and then continue from there. If we can show that that's strictly better than just following through S, then we can throw away S, right? So at the lengths of these tours of segments work out in such a way that even if we make this jump from one side to the other, it's still longer, then we can throw away the original one, right? We know that S is not going to correspond to the shortest path, right? Because if there is one for S, then we can also build one from R that follows R and then jumps across, and then we continue forward from there, right? So that's the idea. Let me spend a little bit of time on a quick example here. So here's an environment, and we'll say the pursuer starts here. On the right, you can see the decomposition we get. In this case, there are 7 regions. And so the pursuer is starting here in region 6. We can just search forward from here. And at this point, you can very clearly tell that the slides were prepared by a graduate student, because they're prepared with a great level of detail and lots of information. So I think that's very nice. Right? So we start with this node, right? So 6 here tells us that we're in conservative region 6. It's this purple one, and then 1, 1 are the gap labels, right? So there are 2 gaps here, one up in this corner, and another over here, right? So we start out in region 6, both gaps contaminated, and then we progress forward from there. Right? So the 2 neighbors of 6 are 5 and 1. So we consider going to each one of those. We compute the gap labels we'll get. In both cases, we get a disappear event. Right? So we can go to region 6. Well, let's see. Okay, yeah, so we go from 6 to 1 or 6 to 5, and we consider both of those. One of those results in being in region 1, with one gap contaminated. One of those results in being in region 5 with the other gap contaminated. Right? And we compute the cost and perform this dominance check, and we add it to the queue. Right? So we can kind of continue from there. And I will actually let me skip through some of this stuff. I think you kind of see the idea here. Keeping track of a queue of possible places we can reach, and for each one, we keep track of the length of the shortest path that reaches that one with the appropriate gap labels here, right? And I guess what we eventually find is that we get to a position where we have, well, in this case, we've reached the end, right? So the solution we finally get is, well, somewhat anticlimactically, to start from region 6 and sort of drive straight across until we sort of take the shortest path to reach this boundary here. And once we hit the boundary between 7 and 2, then the environment is cleared, right? One of which, one gap is already clear, and then that other gap disappears. Right? So that's the basic idea. There's some details omitted here. But doing this kind of forward search, but ordering the search based on the lengths of these tours of segments ends up giving us the result we want. So here's what it looks like when you compare the paths we get. So here's one problem instance that's, well, to be fair, we specifically designed to make the existing algorithm look really bad. So in this environment, here's the visibility cell decomposition. You see it kind of makes this sort of grid structure. And here's the path we got from the algorithm that existed before. So starting from here, it goes down to the bottom and does this sort of zigzag. And there's, just looking at it, there doesn't appear to be any sort of sense to it, right? Right, so the solution is actually based on a breadth-first search through that information graph that we saw before. Right? So it minimizes the number of cells we visit, but the paths we take through some of those cells may be longer than they need to be. Okay, so we thought about comparing our result to theirs, and that didn't seem quite fair since they're not making any attempt to be optimal. Right? They're just picking centroids and driving to them. Right? So to get a slightly more of an apples-to-apples comparison, we took their solution and found the shortest tour of segments that follow the same sequence of conservative regions that they did. And you can see that helps a little bit. We lose all this jagged behavior. Instead, it sort of cuts across here at these intersection points. I'm not sure if you can see those. Right, but it's still doing all this travel that's not strictly necessary, right? So the message you can take from these bottom two is that it's not enough just to find a sequence of regions and then optimize the path you take through those regions. You really do need to consider your optimality constraint from the very beginning when you're choosing which regions to visit, right? So here, in this case, we end up cutting across sort of all these regions to clear this gap over here, whereas sort of the classical algorithm would make a very long trek down here to clear it at this point, right? Instead of the much shorter one that crosses more regions over here, right? So you can kind of see that they're inseparable. We need to think about optimality from the very beginning if we want to have any hope of finding an optimal solution. Okay.
And it's the dominance thing that keeps you from having to visit all those guys down at the bottom?
Yes, well, it's the dominance thing that keeps you from considering all. So if you treat your set of conservative regions as an alphabet, right? It feels not quite, but a little bit like sigma star, right? So the dominance is what keeps the search from taking actually literally forever. Right? So otherwise, you have no way of knowing that going from region A to B to A to B to A to B to A to B, right? The dominance will catch that and say, "No, look, you're spinning your wheels." So without that, the search will continue thinking of longer and longer sequences without.
Let me ask another question. Going back to the previous slide, there comes a point where so in the lower right, there comes a point where it bounces. It appears to suddenly make this turn.
Yes.
And the question is, what defines the point where it makes that turn and the angle at which it turns? It looks like there's like you're reflecting against one of these.
Yes, it absolutely is. Right. So I can give just I would have to do some studying to give you the complete algorithm, but I can give you just a little bit of intuition. So suppose we wanted to do this for, let's say we have a start point, and we want to hit one segment, and then we have a final point, right? And think of the final point as a query point, right? So the question is, what does the shortest path look like? So if our query point is here, then the shortest path is very easy, right? There, right? If our query point is over here, then the shortest path, I guess, should go to this endpoint and then turn. Right? And the other possibility is if the query point is down here, then that's where we bounce. Right? So we go here and bounce. And if I'm remembering correctly, it's computed so that these angles are equal. So that's the idea. Since I've drawn this much, let me just draw the rest of it. This actually gives us a subdivision of the plane. So we can subdivide the plane into essentially 4 regions. So there's the pass-through, right, where we just sort of ignore that segment, essentially. We have some other region where we make a left turn. I didn't show an example, but there's also a right turn, and then we call this a bounce. Right, so this behavior is what's generating this. So it's bouncing off of that segment extended down this way. Okay, that's actually an excellent question. Okay, so can I say anything else about this general algorithm?
Do you need more space than the gap navigation tree?
More space than the gap navigation tree? Yes, in fact, you may all have noticed a distinct lack of any big O's in my description of the algorithm so far. That is a problem we are still working on. I can tell you, yes, more than the gap navigation tree. Your follow-up question of how much do you need, we don't know yet, actually. This is one that's been actually surprisingly difficult to get even very, very loose bounds on the runtime. If you have any good ideas about how to analyze this, then I'm interested to talk. But yeah, I mean, the problem is so different that maybe it's not a surprise that this needs quite a bit more than the gap navigation tree. Okay, anything else I can say about this? Okay, so let me say at least a little bit about multiple robots. So there's some more examples here. The summary is it works, right? And it can actually make some very big improvements over the classical algorithm. Okay, so we talked a little bit already about multiple robots. One very natural reason we need to think about multiple robots is if there are holes in our polygon, right? If you've got holes, then I can give you a very simple algorithm for deciding whether one robot can solve it, right? The algorithm is return false, right? And you can see why, right? Since the evaders can move as fast as they want, then for any hole, they can spend all of their time on the opposite side of the hole from me, right? So we have no hope of solving that, right? But if we have multiple robots, then we've got a chance, right? So that's kind of where we'd like to go. Of course, there's some trouble because if we have multiple robots, then it's not so clear how to perform the same kind of subdivision, right? Even for simple environments, to keep track of where the evaders might be hiding behind holes and around, turns out this visibility cell decomposition approach falls apart immediately, even with just 2 robots, right? So that idea that we wanted to find some very nice decomposition of the plane and search for a sequence of regions in that decomposition, that is all out the window if we have multiple robots, right? So instead, what we like to think about is searching for a path through through a space I will call the joint configuration space of these pursuers. Right? So rather than thinking about a path through a space of dimension 2 with n pursuers, I want to think about a path through a space of dimension 2n. Right? So some higher dimensional space in which one point in that space tells me where all of the robots are. Right? So if you want, you could think of, for two robots, take the Cartesian product of the environment with itself. Right? And I do realize that already that's 4 dimensions, so it's very hard to visualize. That's why I'm not going to draw any of these things in the slide. Right? So that's the idea. Right? Instead of decomposing the plane, I want to decompose this 2n dimensional space. Right? And I want to find analogs to all those ideas that we had for decomposing the plane. Right? Okay, so that's the idea. If we find the right decomposition, then all the other things that we had before follow through fairly directly. Right? We'll still have appears, disappears, splits, and merges, and all of these kinds of things that we're used to. But they'll be happening as we search through R2n instead of R2. Okay, so here's the basic idea. So here's a very simple example where there's 2 robots, and you can see there are 3 gaps. I would like to classify each of the vertices of those gaps into 4 categories. So we may have some vertices of those gaps that are type 1 vertices. That's just an environment vertex. We'll have some that are environment vertices that are sort of participating in creating the gap, right? So this is when we're calling this an occlusion ray. When that hits a reflex vertex, then we'll call that a type 2 vertex. We also can think about endpoints, right? So type 3 happens when the visibility ray reaches the environment boundary. And here's where it starts to get interesting. When 2 robots are jointly viewing some part of the environment, their rays can intersect, right? So here, robot 1 has its visibility obscured here. Robot 2 has its visibility obscured here. And those 2 points intersect, right? So given the environment and the positions of the robots within that environment, we can find the gaps, and we can label each one of those vertices using these 4 labels. Nothing special about these other than to make it convenient to talk about how these things can change. Right? Okay, so here's the idea. As the pursuers move, for the most part, these gaps are going to change continuously. Right? So pursuer 1 moves a little bit this way, then that type 3 vertex at the top will move slightly to the right. Right? So there's sort of this smooth movement the robots make. And as the gaps change through those movements, we can just think about what happens when 2 of those vertices touch each other. Right? So I want to talk about how the gap boundaries change as the pursuers move. Right? So for example, as pursuer 1 moves this way, there's those 2 type 3 events. Right? If pursuer 1 moves more than a very small distance in this direction, then those 2 3s at the top will merge together and become a type 4 vertex. Right? So there's 2 occlusion rays like this. Eventually they'll cross, and at that point the evaders will be able to, or the pursuers will be able to see up above where that intersection occurs. Right? So that's the idea. Right? We want to think about the kinds of events that can happen when different categories of these gap boundary vertices merge with each other as the pursuers move. Right? So we've got 4 types of vertices. So we have 4 choose 2 different kinds of events to think about, right? So we can sort of enumerate all of those kinds of things. Okay, so let me go through these fairly quickly. You can get sort of the idea. So what happens, or under what conditions do we have a 1 vertex merging with a 1 vertex? The answer is that never happens because 1 vertices don't move. Okay, so that was easy. That one never happens. When does a 2 vertex merge with a 1? Never, right? Those are both environment vertices. Environment vertices don't move, so that never happens. Now it starts to get interesting, right? So we can think about a case where a type 1 and a type 3 vertex merge with each other, right? So this is sort of the view right before, and then you imagine the pursuer moving up, right? So right at that point we have sort of undefined. We have type 1 and type 3 at the same time. But then afterwards, the 3 and the 1 have merged into a 3. Right? So what we're looking for is is a description of the precise configurations where this can happen. Right? I want to write down an equation that says this kind of event happens when the pursuer's positions satisfy blank. Right? And it turns out this is fairly easy. You might recognize this from your linear algebra or from the first day of computational geometry class. Basically, we need the pursuer collinear with the type 1 vertex and the type 2 vertex that's hiding it. Right? Key thing here is that we have two variables and a polynomial of degree 1 on those two variables. Right? Okay, so we can think about that, and as you might imagine, there's a bunch of other slides I have describing those other 7 cases that I haven't mentioned. So let me just kind of flash these here so that you believe that I've thought about all of them. Things start to get interesting. Okay, I'll mention this one just a little bit. This is the case we talked about before, right? So as the two pursuers P and Q move around, those type 3 vertices can move, and the question is when do they meet and merge into something else? And it turns out that happens specifically when when the occlusion rate for P and the occlusion rate for Q intersect. Right, so to get that to happen, we need 3 lines to meet at a single point. Right, so those 3 need to be coincident. 2 of those lines are defined by the variables P and Q. One of those lines is a constant that doesn't move. That's the environment boundary. Right. So here we get an equation in 4 variables of degree 2. Right. We keep going through all of these kinds of things. This is the nastiest case because it depends on 3 robots interacting with one another. Right. So in this case, sort of one robot is essentially sweeping around and moving a gap away from where another robot can see it. So in this case, we get 3 robots interacting, so 6 variables and a cubic equation. Right? So that's kind of bad news. Okay, so here's the good news, right? If we compute all of those things, right, so something like n cubed time to write down all those constraints or all those critical boundaries. Once we've done that, we've got this series of equations that describe surfaces in our 2n dimensional space. And from that point, we can start to think about decomposition, right? And from there, this sort of, at that point, ends the innovation for our algorithms, and we just sort of reach into our toolbox, right? It's known, at least in theory, it's known how to decompose n-dimensional spaces where the boundaries are described by polynomials, right? The tool is cylindrical algebraic decomposition, and right, so well, I'm actually running short on time, so let me just kind of summarize. It's kind of based on these projections where we draw the right kinds of vertical lines at the critical points. And then, given that decomposition, we can form a graph just as we did before, right? So if there are 2 adjacent cells, we draw the edges, we figure out whether there appears, disappears, splits, or merges. One thing that's new here is that we can get nothing events. Right? So this is a case, right? So this red line here would end up being drawn in by the cylindrical algebraic decomposition, but it corresponds to absolutely no event for the pursuer P sort of moving up here, right? So you have to be very careful not to assume that anything in particular is going to happen, right? So this is sort of an unwelcome artifact from the fact that we're using these standard tools to do the decomposition. Okay, so and then we sort of search for a path, right? Okay, so I didn't give you any big O's for the other one. We did our best to give a bound here for how long this algorithm would take. Yeah, don't waste too many brain cycles trying to parse the train wreck of big O's here. So to summarize, it's doubly exponential in the number of pursuers, right? It's not clear whether we can do any better in general. To summarize even more, yeah, we are sad about those results. Okay, so you might ask, well, this is okay. Actually, maybe this crowd wouldn't ask, but when I present this to robotics researchers, question always is, this algorithm is way too slow. You didn't even bother to implement it. Why should we care? Right, so I would claim that that it may be very useful to know where those critical boundaries are, right? And there may be some nice things we can do, maybe not improving the big O's by much, but for practical purposes, we may be able to use those critical boundaries to reason very efficiently about how those gaps change as the robots move around. So let me give you an example. So the question is, can sampling help? Those of you that know motion planning know that there are lots of algorithms that for practical purposes use some random samples and some approximate nearest neighbors to compute paths very quickly in typical cases. So we have a question, can we use sampling to do that? So we're thinking about algorithms that are very much in the same spirit as those classic motion planning algorithms. Right? So the idea is we're choosing some random samples from this 2n dimensional space and trying to draw edges between them, and then sort of propagating forward the edge labels correctly. And we can prove that as long as we do something sensible for sampling, that the probability of finding a solution, if one exists, approaches 1 as the number of samples increases. But what we don't know, this is kind of a big open question for us, is can we find a smart way to choose those samples? Right? And it looks like I'm out of time, so I'll stop there and maybe answer any questions you might have.
Usually, global information is mapped to design an algorithm for it.
Oh, I see. So, all the algorithms I've talked about today started from the assumption that we have global information. Right? So, step 1, given a map, right? Given the whole map, sort of coordinates of each vertex listed in order around the boundary. If you've got holes, maybe the right kind of doubly connected edge list. And so, most of the operations we do are fairly local, but not all of them. Right? So this kind of thing where we for example, if we have, that's not going to work. If we have an obstacle like this, for example, that's terrible. Okay, so if we have an obstacle that looks like this, then that obstacle vertex has a very global effect, right? Even far, far away, a robot over here needs to care about the shape over there, because the gaps are changing, right? Now, if you, for example, if you start to think about variants of this problem where the sensing range is limited, then you get more of a local effect, and I think you have a better shot at it. But as I've described here, you've got to have the global view, and you need to be able to think about these effects that happen sort of even very far away. Okay. Any other questions? Yes.
They try to minimize the number of robots needed locally.
Oh, I see.
And I think the global version is
Yeah, that's easy to believe, right? So let me describe what I think might be an important difference. I don't know exactly which paper you're talking about. But the one thing that's unique about what I'm describing here for multiple robots that I haven't seen anywhere else is the fact that this algorithm is complete. Right? So there are lots of folks, especially in robotics, that describe various kinds of strategies for coordinating the motions of robots. And you sort of cross your fingers and hope it works, right? This algorithm, even though its runtime is so slow that it makes us very, very sad, has the nice property that if a solution exists, this algorithm will find it, right? And it doesn't rely on any specific assumptions about how the robots will work together, right? So for example, there's this huge family of algorithms that says we'll use our robots as guards, right? Well, I'll place one robot at a junction point to prevent recontaminations, right? So in the completely apolitical example that I drew, you can solve that with two robots by dropping one in the middle to prevent recontamination, and then the other robot sort of clears all four, right? So there's lots of work that makes various constraints on the kinds of paths you take for the kinds of coordinated paths you take for all those robots. As far as I know, I mean, maybe there's other work that you've seen I haven't, so let's talk about it. But as far as I know, we're the only ones who are able to say this algorithm is complete, right? If there's any possible way for these robots to work together to clear the polygon, then we're going to find it. So hopefully that helps. David?
So what I'm wondering about is this. Suppose that so obviously the nice thing about your algorithm is it's complete.
Yes.
But obviously the running time is very high. Suppose that someone were to give me the information, perhaps, that there exists a solution of, I'm not quite sure how to phrase this, but there's like a solution of kind of low description complexity or something like this.
Yes.
If I had the knowledge of the existence of a simple solution, is there any way to exploit that fact to perhaps produce an algorithm or maybe a
I see.
the running time of your algorithm
Yes.
might be low, or maybe if I gave it lots of,
Yes.
if I gave it like 3 more guards or something like this to work with, I gave it some extra power, maybe I told you that the solution, uses some very weak form of visibility. I'm not sure.
Yeah, so it's easy to believe that there's a large family of such results that have either been proven or are waiting to be proven.
Yeah.
In particular, so you can imagine. You could imagine knowing, for example, that the solution path follows certain nice rules, where the solution path doesn't do X, or it doesn't require close coordination, right? Or perhaps one thing that comes up in motion planning a lot is the idea that there's a tube through which the solution follows, right? So perhaps if you tell me ahead of time that there's a tube of radius r around some solution, that might make it easier. Particularly, again, I'm sort of mixing metaphors here, but if you're thinking in terms of sampling, then if you've got a fat tube, then it's more likely that you'll be able to get samples that fall in the places where you need them. So, short answer is yes. But a more detailed answer seems harder for me to give at this point.
How much space is still good when you're designing algorithms for
So algorithms for robots are algorithms for computers, right? So I would say that that any space you're willing to put up with for any non-robotics algorithm, that's okay too here, right? When I see something like this, I don't bother writing down the space requirements. Right? Although I think they are, off the top of my head, I think they're similarly bad. Right? One thing that's interesting here is that these are runtimes to compute the plan, right? But when you're done, you have just a path, right? So you can describe that as a sequence of waypoints that each robot should visit, and the robots themselves don't need to do all of this. They don't need to store the whole CAD. They just need to know I should go here at this time, here at this time, here at that time, right? So on the robots themselves, it's very easy to do, right? So all of this, I don't consider the rules of the game to be any different for robotics than they are for any other kind of problem.
So the only purpose of minimal sensing is reducing the number of sensors and
Okay. So, so reducing the price is nice, right? But maybe we can wait 6 months and the prices will come down anyway, right? I think it's more important to say that we want to think about minimal sensing as a way of understanding the problem itself. Right? So, this gap navigation tree to me is a very, very clear example of how this works. Right? The gap navigation tree says, maybe you can invest some more money so I'm saying money again, but maybe you can do some research for a few years, trying to improve sensor technology, to measure distances very, very finely, reduce the amount of noise, try to cancel these things out. The result from the gap navigation tree says, no, don't spend your time on that. Spend your time on very accurately being able to detect when there's a gap. Right? So if you're asking me, the reason for thinking about minimal sensing is to find out which pieces of information that we might try to sense are actually important to the problem. Right? Is that an answer to the question, or if I talked for a long time about a question you didn't ask? Okay, thank you. Any other questions? Or is this the awkward silence where no one wants to ask a question and delay lunch any longer? Okay, thanks very much for your attention. I'll see you tomorrow.